We're in lecture 20 and we're talking about further results associated with Lyapunov stability, and also we're going to be looking at signal properties in preparation to discuss the notion of bounded input, bounded output stability. So here we are. We're looking at applications of Lyapunov's method. We're going to also talk about Lyapunov's indirect method, and then again introduction to Bibo stability. Here are some applications of the Lyapunov theory: linear differential inclusions, uncertain systems, stability margins. We can analyze all of these using Lyapunov theory for linear time invariant systems. So, linear differential inclusions. Suppose you have a set of matrices, and these we can consider the vertices of a system, of an uncertain system. So the system is not completely uncertain. It lies within a set of systems. So the convex hull of this set. So this is a set of matrices. We can consider them like vertices of a polygon. The convex hull is everything contained within those vertices. So basically it's a linear combination of these matrices, but not just any kind of linear combination. This is actually called a simplex, where the alphas here are positive number, non-negative numbers that add up to 1. So if, for example, if we were at the vertex AM, that would correspond to alpha M being 1 and all the others being 0, and so forth. So in this way, we can describe the interior of the space of n by n matrices marked by these vertices. And so we have a system x dot is equal to ax, where a is some element of this set. Okay, so it turns out that a fuzzy logic system can be described by this kind of linear differential inclusion. So this is why it's a useful thing, because we sometimes want to analyze things like fuzzy systems for stability. Okay, so how do we check to see whether the system described by that linear differential inclusion is stable or not? Because we don't know exactly what A is, we can't say specifically anything about the system, but we can determine whether that entire set is stable. And here's one way. This way is not necessarily the best way, but it is a way of checking for stability. So if there is a positive definite P and Q such that this inequality, linear matrix inequality, is satisfied for all of the vertices, all the vertex matrices, then we use this candidate Lyapunov function, and we can show that the derivative along the trajectory can be expressed this way. In terms of the alpha i's, you have a sum of these guys. Okay, but this is strictly less than minus q for all I, so we can replace this with minus q, and it's the same q in all cases, so we can take that out of the summation, and then we just sum the alphas, but the sum of the alphas is just equal to 1, and so we just get this, and this is negative definite. So if we can find such a P and Q, then we can show that any combination like this can be shown to be stable. Okay, so here we haven't picked a specific example, specific A within the set. We've chosen we've chosen one in general, and so it applies to every element in the entire set. So this is how we can use Lyapunov theory to establish the stability of a system like that. Okay, suppose now that A is Hurwitz, but our actual A matrix is perturbed by some delta, where delta is in some set. Okay, so for example, the set can be the set of real n by n matrices with norm less than or equal to some number gamma. Okay, so that's the uncertainty set. And suppose now there exists positive definite P and Q such that this inequality holds, and this inequality holds for the deltas. Okay, so if if that's the case, then you can show that this quadratic Lyapunov candidate, when we plug it in, we get this quantity. Notice I can isolate the parts that involve A, isolate the parts that involve delta, and so all of this comes out to be less than or equal to 0. So this is negative semi-definite, and so we can talk about stability in the sense of Lyapunov for this system. So this is a couple of ways we can work with this to establish stability. Suppose now we want to establish a stability margin. So we have this matrix where the nominal A is known, and then you have the perturbation, which is unknown. And we want to find the smallest, we want to find gamma to be the smallest over all n by n deltas, where gamma is the norm of delta, such that A plus delta is unstable. We want to find the smallest delta that makes A plus delta unstable. So that's a kind of stability margin. How large can delta be? Or rather, how small can delta be and still be and make it unstable? Is basically what this is saying. So for a given matrix, how would you compute this? So it turns out this is not a realistic problem, but it's a good place to start because we don't usually have the whole A matrix being uncertain. Usually we have a structured uncertainty, like we've seen before. Okay, we know the solution to the structured uncertainty problem. It's related to the structured singular value. So now the matrix, if the matrix is not Hurwitz, so for some delta 1, that means there must be some constant alpha 1 somewhere between 0 and 1. So obviously if alpha 1 is 0, then this quantity is just 0. So we get back to alpha A0, which is Hurwitz. So we know that if alpha, this should say alpha 1 here. Oh, I see. Alpha 1, notice this is alpha, where alpha is any number between 0 and alpha 1. Okay, so that's Hurwitz. Now, the eigenvalues of this matrix vary continuously as a function of alpha. So the process of evaluating that is called the root locus. The roots of the characteristic polynomial vary with respect to that gain. On the boundary between stability and instability, there must be eigenvalues that lie on the imaginary axis. So if you look at a root locus, basically as you vary some parameter, the roots migrate. And if it starts off being stable, things in the left half plane, then in order for it to get into the right half plane, it has to cross the imaginary axis. So at some point there must be some alpha such that the eigenvalues of that matrix lie on the imaginary axis. And so the matrix delta that gives the minimum value of gamma must make A plus delta have eigenvalues strictly on the imaginary axis. Okay, so here's another stability margin. Instead of having real values, now we have complex values. And in general, because this is a larger set that we're minimizing over, you will in general get smaller norm values. Again, this is also not a realistic problem because our system is never going to have complex things. It's always going to have real things. But it gives us a place to start. So suppose this matrix has imaginary eigenvalues. Then there's some omega naught such that j omega, so this is like S, I minus this matrix. This has determinant equal to 0. And so we know that A is stable, A naught is stable, and so this determinant is not 0 because j omega is not an eigenvalue of A. And so we know that that is not 0. And so we've seen this kind of problem before. The smallest delta that makes this have determinant 0 is given by this. Okay, so it's given by the smallest singular value of this matrix. So this matrix is not 0, so it will have a smallest singular value that's not 0. Okay, Lyapunov theory can also be used to give us, in addition to stability, other properties of a system. So it's these are some important things. And so a lot of these things can be described by linear matrix inequalities. So for example, suppose there is some positive definite matrix P that satisfies this inequality. Okay, so notice here's our system matrix transpose times this matrix, that matrix times the system matrix. So this is kind of like the derivative along a system trajectory. And this whole quantity is negative. So the system with this transfer function then, if there is a P that satisfies this, then the system with this transfer function is said to be strictly positive real. That means the transfer function plus the conjugate of the transfer function evaluated on the imaginary axis is strictly positive and real. It's a real quantity. So this is going to be a real quantity. Whenever you take a complex number plus its conjugate, that will give you a real thing. But this is not only real, but positive. And it turns out that systems that are strictly positive real have special properties when it comes to designing controllers for them. It turns out those are the easiest and the most reliable systems in which to design controllers for. Okay, here's another stability plus property. Suppose now we have a P positive definite such that this inequality is satisfied. Notice that this is more like a discrete time thing where we have the something transpose something minus the something. Okay, so if we have this kind of inequality satisfied for some P, notice this looks very much like what we saw before with the continuous time system and the strictly positive real. But instead, now in discrete time, if we have this and if the transfer function is given by this, then the system described by this transfer function is bounded real. As opposed to strictly positive real, it's bounded real. So what does that mean? That means the transfer function times its conjugate is less than the identity matrix. So this is going to be a positive semi-definite thing for all values of omega. And so what this is this is kind of like the norm squared, or this is also the kind of thing that's used in evaluating the singular values. So what this says is that all the singular values of the transfer function are strictly less than 1. Okay, so this kind of inequality can be used for a discrete time system to identify bounded real. We're going to come back later and see the value of bounded real systems. And so notice this is like a Lyapunov kind of thing, but it's obviously different because I don't just have the P. So the P matrix is not just any P. It has a very special form, a very structured form here. And the A matrix is not just the A matrix for a system. It's the entire system matrix. So that's very different.